Hello everyone. In this lesson we'll discuss logarithmic functions. Previously we talked about exponential functions, y equals a to the x, that was the general form, and natural exponential functions, y equals e to the x. Recall the inverse of a function y is equal to f of x, then x equals f inverse of y, and x is equal to f inverse of the f of x, and y equals f inverse, or the f of f inverse y, vice versa. Definition: the inverse of an exponential function f of x equals e to the x is a natural log function x equals ln y, or ln of y. So if y equals e to the x, then x equals ln of y, and ln of e to the x equals x. That is because these are inverse functions operating on each other, and whenever an inverse function operates on the other, then the result is your original input, which in this case is x. And e to the ln of x equals x. Again, the same idea from inverse functions operating on each other. If y equals e to the third, then ln of y equals 3, and 3 is the exponent you raise e to in order to get y. Okay, so let's look at some examples. First one, solve for x, y equals 5 raised to the x. Now y is equal to 5 raised to the x. You want to find x, so we can use the inverse function. That is, we can take ln both sides. We take ln of both sides, we have ln of y equals ln of 5 raised to the x. Then we can apply a property of logs to the right side. So we apply a log property, and that log property is based on the exponents. 5 to the x, you can bring this x to the front, so that makes x ln of 5. And now we can divide both sides by ln of 5 to have x remaining by itself. So divide both sides by ln of 5. We end up with x is equal to ln of y over ln of 5. It is typical, if we're taking the log of just a single item, to write ln space that item like this. Could be written ln space y, or we could write the arguments in parentheses. Okay, second problem is solving for x. Ln of 3x plus 1, ln of 3x plus 1, 3x plus 1 is our argument, equals 2. Again, we want to use inverse operation to undo the ln. And in this case, the inverse of ln is e, so we take e both sides, or exponentiate both sides. If we exponentiate both sides, we will have e to the ln of 3x plus 1 equals e to the second. And now this e will undo the ln. Inverse functions undo each other. So we have on the right side 3x plus 1 equals e to the second. Now we want to do some algebra here until we find x, so we subtract 1 both sides. So we're left with 3x equals e squared minus 1, and then dividing both sides by 3, we're left with x is equal to e squared minus 1 over 3, and that is our final answer, and we have solved for x. Now, we have talked about logarithms base e, and that was the ln. Now there are other logarithms apart from base e, and if we denote logs to any base by letter a, so we can say y is equal to a to the x. That was your general exponential function. The inverse can be written y is equal to log base a of x. The number y, that is log base a of x, represents or corresponds to the exponent in the exponential form. In other words, log base a of x is the exponent to which a is raised to obtain x. And so this is what people refer to or are referring to when they say logs are exponents. Now let's use these ideas to convert from log form to exponential form. We know that if we say log base a to, let's say, x equals y, then that means that a to the y is equal to x, right? So here's an idea. The idea is that we can think of this a being your base raised to y to be equal to x. Okay, so think of it going more like a circular fashion or more like a fishhook fashion. Then a to the y equals x. So to the y to the equals. So that's a way of looking at it. Okay, so if we have a logarithmic form, log base 5, u equals 2, so you'll be thinking of 5, 2, the second equals u, right? And that is your exponential form. Again, log base b8 equals 3, so that will be b to the 3 equals 8, and so on. Log p q r equals log pq, so p to the r equals q, right? And log 4 2t plus 3 equals w, so 4 to the w equals 2t plus 3, and we can always convert from logs to exponents using this form. So whatever is on the log side is your base, and your argument, which will be like your output if you're thinking about it in exponential form. So 3 to the 5z, 5 plus 2z equals x for that last exponential. Let's look at an example. We want to change from exponential form to logarithmic form. Now, 3 squared equals 9. So this exponent right here, 2, will go on your right side. Let's put it on the right side. So this is our exponent. 3 is our base. The 9 would be your argument. So log base 3 argument 9 equals 2. That means if we did like we did previously, to say 3 to the second equals 9. Okay, and that is how you do your conversion from exponential form to log form. From log form to exponential form, we have example here, log base 464 equals 3. Again, think of it going 4 to the third equals 64, and then that is your exponential form. So what this means is 4 to the third power equals 64, and we are done converting from log form to exponential form. Now let's look at some more general properties of logs. Previously, we learned some properties saying that log a argument 1 equals 0. That means a to the 0 equals 1 if you're converting it to exponential form, which is here. An example, log base 2 of 1 equals 0. The second property is log a, the argument a equals 1. That means a to the 1 equals a. Example, log 10, a log base 10. Usually if we have a log base 10, we tend not to write the 10 right here. Of 10 equals 1. Next one is log base a of a raised to the x equals x. And the reason is that a to the x is equal to a to the x. So you're raising a raised to the x be equal to a to the x. Right? And then a log base a of x equals x. And this we can get from our inverse operations, which we just identified previously. Okay. Let's talk about a theorem. Log functions are one-to-one, and if we can remember our general exponential function, which was one-to-one, and then think of your inverse being your log function. It's also one-to-one. So this is your log function. That was your exponential function. Then we can use these ideas to do some algebra, a bunch of algebra, right? For positive real numbers, x sub 1 and x sub 2, if x sub 1 is not equal to x sub 2, then log base a of x sub 1 is not equal to log base a of x sub 2. And if log base a of x sub 1 is equal to log base a of x sub 2, then x sub 1 equals x sub 2, right? That is true for a one-to-one function. Now if we have to solve the equation, an example, log base 6 for x minus 5 equals log base 6 of 2x plus 1. Notice the logs are the same, right? The bases are the same, log base 6. So therefore, the arguments should be equal. So the same log base, then that means the arguments are equal. Okay. So let's equate them and see what happens. We have 4x minus 5 is equal to 2x minus or plus 1. Let's do some algebra. Subtract 2x from both sides, and we're left with 2x minus 5 equals 1. Then add 5 to both sides. We're left with 2x equals 6. And divide both sides by 2. And we get finally an answer for x. X equals 3. Okay, so that is how you would solve a problem like this. Alrighty, so let's talk about common logarithms and natural logarithms. Common logarithms are logs base 10. So common logarithms, log base 10, log base 10 is common. It's what we call common logarithms. And these properties of general properties of logs can be extended to common logarithms and to natural logarithms. Right? So all the properties that we met before can now be applied to all logarithms. Right? Remember to like, subscribe, and see you next lesson.